right now, your text messages, your bank data, your passwords, they're all protected by math.
Yeah, very complex math, sure, but ultimately it's just math.
Exactly. Math that a sufficiently advanced computer, like, say, a future quantum computer, will eventually just chew through in seconds.
Right, which is a terrifying thought for cybersecurity.
It really is. But what if you could protect your data not with math, but with the fundamental laws of
I mean,
physics?
that completely flips the script on how we handle security.
Right. So instead of a digital file that anyone can just hit, copy and paste to duplicate, imagine building a digital vault out of something like a soap bubble.
A vault that literally physically shatters if a hacker even looks at it.
Yes, which is exactly why we are doing this deep dive today. Our mission for you listening is to explore this brand new breakthrough paper called Unconditional Unclonable Encryption.
By Prabhanjan Ananth from UC Santa Barbara and Amit Sahai from UCLA.
Right. And we're going to look under the hood of what might actually be the holy grail of quantum cryptography.
Without getting buried in the equations, hopefully.
Yes, I promise we'll keep the math to a minimum, but you will want to stick around for the end because the way this paper was actually written involves a plot twist that, frankly, I genuinely did not see coming.
It's a pretty wild detail, yeah. But to appreciate the breakthrough, we really have to start with the core phenomenon the authors are exploiting here, which is the no-cloning principle in quantum mechanics.
Okay, let me see if I have this right. The no-cloning principle essentially says that you just cannot perfectly copy an unknown quantum state.
You've hit the exact core of it. I mean, in the classical digital world, if you don't know what a file contains, you can still just copy it bit by bit.
Right, like zeros and ones are robust. You can copy a hard drive without knowing what's on it.
Exactly. But a quantum system, like an electron's spin or a photon's polarization, it exists in this really delicate, undefined state until you measure it.
Like the soap bubble.
Right. If you don't already know the exact state it was prepared in, the mere act of measuring it to try and create a copy will, inevitably force it to collapse.
So you irreparably alter the original state.
Yeah, you end up destroying the original just to get a flawed copy. So unclonable encryption basically takes this apparent bug of quantum fragility and turns it into the ultimate security feature.
So instead of trying to make the quantum state stronger, they're using its fragility as a booby trap.
That is exactly what they're doing.
Okay, but how does the paper actually test this? Because reading through the setup, they construct this very specific, really high-stakes scenario to prove their encryption works.
Yeah, they focus on a one-time setting that's designed to test the absolute limits of physics. So picture an encryptor who sends a single message wrapped in these fragile quantum states.
Right, so a quantum ciphertext.
Yes. Now, an adversary intercepts this ciphertext while it's traveling. But crucially, at this exact moment, the adversary does not have the decryption key.
Okay, so they just have this weird quantum soap bubble box. They can't open it, and they know if they try to pry it open without the key, it pops.
That is the situation. So the adversary tries a completely different tactic. They decide to split the quantum ciphertext between two separate non-communicating recipients.
And in cryptography, we usually call them Bob and Charlie, right?
The famous Bob and Charlie, exactly.
Wait, but if I'm the hacker, why am I giving the box to two other people who can't talk to each other? Like, what does that actually achieve?
Well, it's about testing the bounds of information duplication. The adversary splits the quantum state, sending part to Bob and part to Charlie, essentially trying to cheat the no-cloning theorem.
Oh, I see.
Yeah, the goal is to see if Bob and Charlie can somehow both extract the original information. And to make it a true test, later on, the actual decryption key is publicly revealed to both of them.
So they both get the key at the end.
Right. And the absolute gold standard for security here dictates that Bob and Charlie cannot both simultaneously recover the hidden message.
Ah, okay. So if Bob's piece of the state yields the message, Charlie's piece basically has to yield garbage.
Exactly. It's a race, and there can only be one winner.
But how do we mathematically measure if Bob or Charlie actually succeeded?
So historically, researchers measure this using two different standards. The older one is called search security.
Search security, okay.
Yeah, so imagine the hidden message is chosen from a massive pool of possibilities, say 1 million different options. The adversary intercepts the quantum state, splits it to Bob and Charlie, the key is revealed, and both try to guess the exact message.
Right.
Now, a prominent 2020 paper by Broadbent and Lord proved that in this scenario, You could limit Bob and Charlie's simultaneous success rate to a specific mathematical bound.
And that bound is I have it here, the cosine squared of pi over 8.
That's the one.
I mean, I'm looking at those numbers and my brain is just seeing static, so you're going to have to translate that into a real-world percentage for me.
Fair enough. It translates to roughly an 85% success rate.
Wait, 85%? That sounds terrible. If I have a vault and a bank robber has an 85% chance of guessing the combination, I'm finding a new bank.
Yeah, and the cryptography community felt exactly the same way. An 85% chance of an adversary breaking your code is just totally unacceptable.
No kidding.
So the field moved away from search security to a much stricter standard. And this stricter standard is the entire focus of Ananth and Sahai's new paper. It's called Indistinguishability Security.
Indistinguishability security. Okay, let's break that down for the listener.
Okay.
How is that different from searching through a million options?
The concept is wonderfully minimalist, honestly. Instead of a million possible messages, the encryptor randomly chooses to send just one of two options, message 0 or message 1.
Oh, wow, just two options.
Right. So Bob and Charlie just have to guess which of the two is sent.
Hold on, I see a glaring loophole here. Like, if I'm the adversary intercepting this, I can just call up Bob and Charlie and say, hey guys, when the time comes, don't even look at the quantum state. Both of you just guess message 0.
Ah, yes.
Because if the encryptor happened to send message 0, they both win. And they'll be right exactly 50% of the time just by being lazy and guessing blindly.
You've just described the absolute floor of indistinguishability security. Because there are only two options, the baseline success rate is always at least 1/2 or 50% simply by guessing.
Okay, so the goal of this new encryption isn't to get their success rate to 0, because that's impossible when you can just guess.
Exactly. The goal is to ensure they cannot do even a fraction of a percent better than that lazy 50% strategy.
So if they can use the quantum state to guess right, say 50.0001% of the time, the encryption is considered broken.
Correct. You want their success rate to be exactly 50% plus some tiny microscopic margin of error that rapidly shrinks to 0 as your security key gets longer.
And cryptographers call that an exponentially small advantage. Right?
Yes, an exponentially small advantage. Okay, but if the baseline is 50% and we just want to push them down to that floor, why is there an entire graveyard of papers that failed to do this? Like, reading the introduction, it seems like brilliant minds have been slamming into a brick wall for years trying to make this work.
Achieving that indistinguishability security with a negligible advantage is brutally difficult.
Why?
To understand why, we have to look at the compromises previous researchers had to make. Like, some teams actually managed to get the math to work, but only in what cryptographers call idealized models.
Like the quantum random oracle model mentioned in the text.
Exactly.
What makes a model idealized, though? Are they just pretending gravity doesn't exist?
In a way, yeah, kind of. Idealized models are essentially theoretical training wheels. They assume the existence of a perfectly random, universally accessible function.
Like a magic black box.
Right, a magic black box that everyone can interact with. And it's great for proving mathematical concepts in a vacuum, but you can't build a real physical device out of it.
Because that magic black box literally doesn't exist in nature.
Exactly. The true test is making it work in the plane model.
The plane model.
Yeah, which basically represents the harsh reality of actual physics and practical computing. No training wheels.
So when researchers took the training wheels off and went into the plane model, what went wrong?
Oh, they hit a series of massive roadblocks. For instance, there's a paper from 2025 known as AKY25. They achieved the required security, but their scheme required the decryption keys themselves to be made of quantum states.
Wait, which completely defeats the purpose.
Right.
If I need to send you a fragile quantum soap bubble, just so you have the key to unlock the other fragile quantum soap bubble I sent you, how do I securely send the first one?
You've identified the recursive nightmare of quantum keys. Storing and transmitting quantum states without them collapsing is immensely difficult. You need, like, freezing temperatures and vacuum chambers.
Not exactly practical for a smartphone.
No, not at all. We desperately want classical keys, just regular digital strings of zeros and ones on a normal hard drive to unlock the quantum ciphertext.
Did anyone manage to use classical keys before this new paper?
A team known as BBC 26 actually did manage to use classical keys, and they achieved optimal security.
Okay, so what was the problem?
Their scheme had a fatal flaw. It was computationally inefficient.
Inefficient meaning it drains my laptop battery, or inefficient meaning something worse.
Something much, much worse. The encryption and decryption processes took exponential time.
Oh boy.
Yeah. As you made the message slightly more secure, the time it took to run the algorithm just skyrocketed. If you wanted standard cryptographic security, it could theoretically take longer than the lifespan of the universe just to encrypt a simple text file.
Wow. Okay, that's definitely a fatal flaw.
Yeah. And then another group, Botteron and colleagues, they solved the time issue, but their security advantage was incredibly weak. It didn't shrink fast enough, and they could only mathematically verify their scheme up to 17 qubits.
17 qubits. Okay. So it sounds like previous scientists were trying to build a perfectly secure vault, but they either had to make the physical key out of antimatter, or the vault took a billion years to open, or the lock was so flimsy a child could pick it.
That is a highly accurate summary of the field, honestly. And there's actually one more tombstone in that graveyard.
Oh.
Yeah, a very common approach in quantum cryptography relies on what are called BB84 states. They're named after a famous 1984 paper.
Okay.
But a recent paper by Coladangelo, Liu, and Shi mathematically proved that using a direct BB84 approach cannot provide the exponentially small error rate needed for true indistinguishability security.
Oh, wow.
Yeah, BB84 was confirmed to be a dead end for this specific problem.
Okay, so the stage is set, the training wheels are off. The BB84 route is totally blocked. The keys have to be classical digital bits, the encryption has to be instantaneous, and the adversary's advantage has to be mathematically negligible.
Quite the laundry list.
Yeah. So how on earth did Ananth and Sahai pull this off?
Well, the breakthrough was formalized in Theorem 1.1 of their paper. They created a one-time private key quantum encryption scheme. But, and here's the catch, it is designed for a one-bit message.
Wait, just one bit.
Yes.
All of this theoretical physics, breaking the laws of cloning, dodging this entire graveyard of past papers just to securely send a single 0 or a 1. I mean, why should you or I care about that? We send gigabytes of photos and videos every day. A one-bit message seems entirely useless.
I completely understand that reaction. It sounds underwhelming. But in theoretical cryptography, securing a single bit with an exponentially small advantage is the ultimate prize.
Really?
Yeah, think of it like a physicist proving they can split a single atom. You don't ask the physicist why they didn't split an entire apple, right?
Okay, yeah, that makes sense.
Splitting one atom proves you have mastered the underlying mechanics. In cryptography, if you can perfectly secure one bit against quantum cloning attacks, there are already established simple protocols to scale that architecture up to secure an entire hard drive.
Oh.
The astronomically hard part is just getting that first bit right.
Point taken. Atom splitting it is. So what does this one-bit lock actually look like?
Okay, so it uses a classical key made of a specific number of bits. Let's call that number 2, n-1. And the quantum ciphertext is made of n qubits.
Okay.
It's perfectly correct, meaning the legitimate receiver always gets the message. And crucially, it uses efficient, single qubit Clifford gates for encryption and local Pauli measurements for decryption.
Okay, you have to translate Clifford gates and Pauli measurements for us. I'm lost.
No problem. Think of a qubit like a sphere. A Clifford gate is just a basic mathematical operation that rotates that sphere in specific, predictable 90-degree increments.
Okay.
It's basically the quantum equivalent of a simple logic gate in a normal computer. It scrambles the state, but in a way that is highly efficient and really fast to compute.
And what about Pauli measurements?
A Pauli measurement is basically just how you look at the sphere. You can choose to measure its spin from the top down, from the left to right, or from front to back. These are represented by the matrices X, Y, and Z. The paper refers to them as the Pauli family.
Okay, so they're using basic rotations to lock it and basic measurements to unlock it, which solves the billion years to open problem.
Exactly.
But how did they dodge the BB84 dead end? What is the actual mechanism that secures this one bit?
They replaced that standard BB84 method with a concept they call random tensor Pauli parity.
Random tensor Pauli parity. Okay, let's look under the hood of that. How does that hide a 0 or a 1?
So the encryptor takes the classical digital key and uses it to choose a sequence of those Pauli measurements we just talked about, a sequence of X, Y, and Z operations.
Right.
But they add this brilliant twist. The first operation in that sequence is explicitly forced to be an active rotation, so an X or a Y. It is never allowed to be the identity matrix, which would just, leave the qubit alone.
Why does forcing that first move matter so much?
Because it guarantees a specific, rigid mathematical structure across all the qubits. The encryptor then samples random bits and selects a special parity bit. They orchestrate the math so that the message itself, the 0 or the 1, isn't actually stored inside any single qubit.
Wait, then where is it?
Instead, the message is equal to the product of all the eigenvalues of those local Pauli operations combined.
Okay, explain the eigenvalue part.
So if I'm the legitimate receiver with the right classical key, I use that key to perform the correct measurements on my n-qubits. Each measurement gives me a positive or negative sign, a +1 or a -1. And you simply multiply all those signs together. A series of pluses and minuses will ultimately result in either a final plus or a final minus.
And that final sign is your message.
Exact.
That's incredibly elegant. You're literally just multiplying positive and negative numbers. But if the hacker intercepts this and splits the qubits between Bob and Charlie,
The no-cloning theorem completely takes over. Because the message is hidden in the relationship, the parity across the entire structure of the qubits, splitting the state, destroys that Delamy relationship.
Oh.
Yeah, neither Bob nor Charlie will receive a set of qubits that yields the correct sequence of signs. The parity is broken, the message just dissolves into random noise.
and the math backing this up is rock solid. Like, what is the exact limit of the hacker's advantage?
The probability of both Bob and Charlie winning is mathematically proven to be less than or equal to 1/2 plus 2 to the power of -n plus 1/2.
Okay, translating that for the listener. The 1/2 is the 50% lazy guessing floor we talked about earlier.
Right.
And the extra part, the 2 to the negative power, means the advantage they have over a random guess shrinks exponentially for every single qubit you add to the ciphertext.
Yes.
So if you use 100 qubits, their advantage is essentially 0.
It's as close to perfect security as physical laws allow.
But this leads me to a massive question. I'm looking at the paper, and math required to prove that the hacker's advantage is 0 is staggering. There are pages of complex matrices. How do you even prove a negative like that?
It's a huge challenge.
Like, how do you mathematically prove that a hacker, using literally any conceivable quantum trick, cannot extract the message?
Proving security bounds is notoriously difficult, especially here, because when an adversary splits a quantum state, they're applying this dynamic, evolving process, a quantum channel. It's incredibly difficult to analyze a moving target.
Right.
So Ananth and Sahai used a really powerful mathematical technique called the Choi-Miokowski representation.
The Choi-Miokowski representation. Okay, what does that actually do?
It's basically a mathematical trick that converts that dynamic splitting process, the action of the hacker, into a static, fixed tripartite state. It takes a process happening over time and turns it into a single quantum state shared between 3 parties that just, sits there.
Oh, I get it. It's like taking a high-speed, ultra-slow-motion photograph of a bullet hitting an apple.
That is a fantastic analogy, yeah.
Because you can't measure the explosion while it's actively exploding, but if you freeze it in a photograph, you can just take a ruler and measure the exact physics of the shrapnel.
Exactly. By freezing the hacker's channel into a static state, the mathematicians could essentially take a ruler to it. The entire proof then boiled down to finding the absolute mathematical ceiling, the upper bound of a specific operator they call G.
Operator G.
Yeah. If they could prove the size of G was exponentially small, the security was fully guaranteed.
And how did they prove the size of G was practically 0?
They constructed what they called a filtered overlap argument. Without getting bogged down in the algebra, they essentially built a mathematical filter that isolated only the very specific, rare scenarios where Bob and Charlie's measurements might accidentally align. Once they isolated those scenarios, they calculated the total volume of those possibilities and proved that as you add more qubits, that volume shrinks exponentially towards 0. The logic is just airtight.
I mean, it's a monumental achievement in theoretical computer science. Which actually brings us to the plot twist.
A twist, yes.
The jaw-dropping detail buried all the way at the end of the paper's introduction. I'm going to read this directly from the source material under a small heading called Statement on AI Usage.
Go for it.
It says, quote, "The construction and main ideas of the proof were generated entirely by Codex using GPT 5.6 Sol Ultra."
I know. When you read that sentence, it completely recontextualizes the entire paper.
I'm still trying to wrap my head around it. For you listening, we literally just spent this entire deep dive unpacking a fundamental breakthrough in quantum physics, a problem that has baffled brilliant human cryptographers for years, leading to a graveyard of failed attempts.
Yeah.
Only to find out that the eureka moment, the random tensor Pauli parity, the filtered overlap argument, was authored by a machine learning model.
It is a stunning realization. However, to be fair to Ananth and Sahai, we do need to clarify how this actually happened. The statement explicitly notes that the human authors take full responsibility for the claims and the proofs, and they carefully refined and verified the AI's output.
Right.
The AI didn't just quietly print out a flawless 24-page PDF while the researchers were out getting coffee.
So they didn't just type, "Please solve unclonable quantum encryption" into a chat box.
No, the collaboration was much more structured than that. The authors used something called the UCLA Moonshot Harness. It's a framework developed by a large team of researchers, including the renowned mathematician Terence Tao.
Okay, what does a harness do in this context?
Think of it as intellectual scaffolding. It's a sophisticated environment designed to guide AI models through deep, multi-step mathematical reasoning. The human researchers built the harness, they defined the constraints of the plane model, they pointed out the BB84 dead end, and they basically directed the AI toward the goal. Yeah, the humans provided the rigorous verification, but the AI provided the conceptual leap. The AI looked at the constraints and generated the actual architecture that solved the problem.
It is such a profound example of human-AI collaboration. Like, the humans mapped the maze, but the AI found the path to the center.
Exactly. So if we pull back and look at the big picture, what does this actually mean for you, the listener?
Oh, well, let's summarize the journey. We started with the threat of quantum computers breaking traditional math-based encryption. We explored how unclonable encryption uses the extreme fragility of quantum mechanics, the no-cloning principle, to build a vault that physically cannot be duplicated.
Right.
We walked past the graveyard of previous attempts that relied on imaginary training wheels or required impossible quantum keys. We saw how Ananth and Sahai bypassed those failures by using random tensor Pauli parity to hide a message in the mathematical relationship between qubits, ensuring a hacker's advantage shrinks to zero.
And finally, we discovered that this historic proof was actually conceptualized by an artificial intelligence. The value of this breakthrough for the future of privacy is just absolute. Right now, if someone intercepts your encrypted data, they can copy it, save it on a server somewhere, and just wait 10 years until computers are fast enough to break the math.
The steal now, decrypt later attack.
Exactly. But with unclonable encryption, there is no copying. If a hacker intercepts it and tries to split it or save it, the physical state collapses. The data destroys itself. You move from temporary mathematical security to unconditional, permanent physical security.
We have finally designed the perfect soap bubble vault. But, I want to leave you with a final thought to mull over. Something not explicitly discussed in the paper, but honestly deeply unsettling.
Oh.
If an artificial intelligence system like GPT 5.6 Sol Ultra, guided by a harness, can generate the primary theoretical architecture for an uncrackable quantum lock, what happens when a malicious adversary uses that exact same level of AI to search for vulnerabilities in the laws of physics themselves?
That's a scary thought.
Right. If AI can weave the perfect quantum lock, are we entering an era where AI also becomes the ultimate quantum lock picker?